There we go. As long as I don't drift too far over this way, I shouldn't even need a camera person today. So if I start writing on that third board, you know, about 30 minutes from now, do remind me I need to move the camera over to see it. Okay, so let's get started here. Let's talk about graphs of equations. So really, the fundamental thing is, what does the xy plane mean? So if we draw a picture of the xy plane like this and like that, right? And I tell you, here's a point, right? And I tell you that the point is, let me call it P1, and suppose it's like 1, 3. What does that mean? How do we find 1, 3? Put some little tick marks here. I will not be so adventurous as to try to draw a graph on the board. I think in your homework there might be like a graph that's you can see, so you can kind of look at the graph and follow the lines like that, right? But what does that mean? 1, 3. That means we're 1 in the x and 3 in the y, right? We go over 1 and up 3, and that's the location of that point, which I've called P1, right? So another example, what if I had, say, P2 equal to, 2 comma minus 2? Where would that be? We go over 2 and we go down 2, right? That'd be down here. Let's see here, third point, P3. Let's suppose we have minus 4 comma 2. Where would that be? So we go 4 to the left, right? 2, 3, 4, and then we go up 2. So to the limits of my artistry, it's about here. One more example. P4, I'll do, say, minus 3 comma minus 3. So we go 3 to the left, and then we go 3 down. So it's about like right here. Now, the reason I'm giving you 4, you're like, okay, great, I think I know how to plot points in the plane. Hopefully you thought, how many people have never seen plotting points in a plane before? Okay, good. That's good. See, because forgive me if I'm ever insulting in here. I'm not trying to be insulting. I really just don't honestly know your background. I'm new here, and so you need to speak up if I'm talking about something like you feel like is just completely new to this course. You should let me know. All right. What I'm trying to say is, more generally, don't hesitate to jump in and say, "Could you explain that more?" That's fine. So you guys, what quadrant are these different points in? I drew a point 1 in each quadrant here. So point 1 is in quadrant what? Yeah, quadrant 1. So for some reason, we tend to use Roman numerals for quadrants. I don't know why, but this is quadrant 1. Point 2 is in quadrant what? Quadrant what? Quadrant 4. So in Roman in Roman numerals, that's IV, right? Of course, if you said it was in quadrant 4, I would be like, fine, How about point 3? Quadrant 2, right? And finally, quadrant, the fourth point is actually in quadrant 3, right? So it's mostly just important to be aware of this terminology, so you know what people are talking about when they talk about quadrants, right? Okay, so now that we have that settled, what do we mean graph of an equation? What is the graph of an equation? So I'll give you a definition. The graph of an equation is the set of all ordered pairs x comma y which make the equation true. Or you could say which solve the equation. So that's the graph of an equation. What does the graph of an equation look like? Do you guys know? I mean, does that question make sense? How about this? What if we had x squared plus y squared equals to 1? Have you ever seen this equation before? I see some yeses, some nos. So if we've never seen an equation before and we don't have a graphing calculator handy, what can we do to figure out what it looks like? We just do what? We just make a table of values, right? Try plugging in some values, and then we can plot those points. So I'll do that for this equation. So if you think about it, can we have a solution right? So notice that y is going to be plus or minus the square root of 1 minus x squared here. Let me make that bigger. I write too small up here sometimes, and you got to stop me if you're in the back. So if I put x here, I'd put y is, plus or minus square root of 1 minus x squared. The reason I'm saying that is if you look at this equation, right? If we solve for y, we've got y squared equals to 1 minus x squared. So then the way that implies that y is plus or minus the square root of 1 minus x squared. That's some algebra that we can do. So, as you think about putting values in for x, think about that equation. Could x be large? Could x be 2? What would happen if we put x equals to 2 into this equation? Think about plugging 2 into here. What happens with 2? X equals to 2 won't work. X equals to 2 won't do because we've got 4 plus y squared equals to 1, which gives me y squared is equal to minus 3. Y squared equals to minus 3 has no real solutions. Right? I can't get a real number, square it, and get a negative number. So what I'm trying to tell you is if you look at this equation and just think about it for a minute or two, you should understand that if x is going to work, it's going to have to be some number that's between plus or minus 1. So our table of values, we're going to pick x's that are between plus and minus 1. We can also see that must be the case from looking at this, right? Like, if you think about 1 minus x squared, if you had a number bigger than 1 and you plugged it in here, you'd have the square root of a negative number, which wouldn't work for us. Okay, so, you could try to make your table of values starting at 2, but you should figure out when you try to do 2 that it doesn't work, so it's not a solution, All right, so I'll start at minus 1, though. And then I'll go minus 0.5, 0, 0.5, and then 1 again. Let's see what we get from that. So what do you guys get when you plug in -1 into this formula that we found? What's 1 minus 1 squared? Right? Yeah, so we get 0 from the first one. What about when we plug in 0.5? What's 1 minus 0.5 squared? 0.5 squared is 0.25, so we get like plus or minus the square root of 0.75, whatever that is, right? When we plug in 0, we get 1 minus 0 squared, which is 1, so we get plus or minus 1. When you plug in 0.5, you also get plus or minus the square root of 0.75. And finally, when we plug in 1, we again get 0. So I've got 1, 2, 3, 4, 5, 6, 7, 8 points on the graph. Hopefully that'll be enough to see what the shape is. Let's see here. So when x equals to 1, we've got this point right here, 1, 0. When x equals to -1, we've got that point over here, -1, 0. I'll do those to start with because they're the easiest ones. What else is easy? How about the middle case? 0, 0, comma 1, or 0, comma -1, right? I've got so those are 4 points I can see from the table, right? And then I got the more interesting ones, right? Like at a half, it's at plus or minus the square root of 0.75. What is the square root of 0.75? Since this is not a test, I can check with my phone, right? A reminder, can we have our phones out during the test? No, we cannot. So we need to have a calculator which is independent of the phone. So sadly, we will not be doing square root of 0.75. We will not be doing scary 2.75. Why is 3 a.m. so scary? Scary movie 5. Scary movie 5? What? All right, so Google is distracting. We should use something else. Let's try this again. Square root of 0.75. Oh, of course, 0.866. 0.866. Approximately. Now, for what it's worth, guys, this is the square root of 3 over 2. So because the square root of 0.75 is actually the square root of 3 over 4, which is the square root of 3 over the square root of 4, which is the square root of 3 over 2. This is a number that you'll see again, especially in the as you take pre-calculus algebra, like the second semester of pre-calculus algebra, where you do trigonometry, this number comes up a lot. It's a special number. Anyway, 0.866 plus or minus. So let's try to plot these points. We go a half, and then 86% of the way up here, right? So it's about right here. It's about like right here, right? This is 0.5, 0.86 approximately, and minus 0.5, 0.86, and then like symmetrically downstairs here, minus 0.5, minus 0.86, and this guy over here, 0.5, come on, minus 0.86. And then we can try to connect the dots to see what the graph is, right? So, So up to the limits of my artistry, the graph of this equation is it's a circle, right? So in fact, we've just graphed, this is the so-called unit circle. There's an easy way to understand this. Do you guys know the distance formula? How do we figure out how far a point is away from the origin? What's the distance of the point from the origin? The distance from, let's say, x1, y1 to x2, y2, if you want the distance formula. I think this is usually covered in like 6th or 5th grade math, right? Depending on maybe 7th grade, I don't know. It varies. But this is the distance formula. You take the difference of the x coordinates, you square it, and then you take the difference of the y coordinates and you square it. You add those squares together, you take the square root. That gives you the distance from point x1, y1 to point x2, y2. This is how we calculate the distance between 2 points in the plane. So like, what's the distance from the origin to a point xy? So what happens like if your x1, y1 is 0, 0, and I just put x2, y2 just to be xy, what does the distance formula give you? Square root of what? So this is the definition of distance in the plane between 2 points, but it may or may not be in section 2.1, but it really should be there. If it's not, it should be there. Yeah, how does this formula simplify? We get x minus 0, right? Squared plus y minus 0 squared. Can you think of I mean, there's an easier way to write that, right? It's just the square root of x squared plus y squared. Am I right? So this equation, x squared plus y squared equals to 1, how could we look at that? X squared plus y squared equals to 1 is really the same as the square root of x squared plus y squared equals to 1. Nothing is lost because both sides are positive, so I can take a square root and not change the equation. What does that equation say? In words, it says the distance from the origin to the point xy is 1. So that's why the equation of a unit circle is x squared plus y squared equals to 1. It's the equation that is true whenever the point x comma y is distance 1 from the origin. Does that make sense? But of course, we just did a very brute force method of graphing the circle. We just plug points in, right? The plug-in points. So, I appreciate that. What I'm trying to say is that we can interpret that equation in terms of distance. That's all. So it's not surprising what we found with our table of values, right? Absolute. Oh, the square root? No. That's not part of this is not part of the solution to this problem. This is just commentary. This is confusing commentary. I'll label it confusing because apparently it is. But that's one of my goals, is to confuse the students. So I feel like I've mission accomplished. No, all right. Look, so when you're graphing an equation, I think actually pragmatically speaking, oftentimes we actually use some kind of technology to graph, right? So let me show you one technology that I like to use to graph equations, and it'll allow us to see like a bunch of examples. Because honestly, like I can do about like 3 of these in a class period, unless I'm hurrying. But once I start hurrying, then it's pointless, right? So I can show you many more examples of equations if you just let me use the projector here for a couple minutes. And I'll use one of my favorite. There's many choices, but and I'll send you an announcement with a link to this website after class, hopefully. But the website I'm going to use is called Desmos. Desmos.com. It's DESMOS. And essentially what it is just a graphing calculator app. Well, it's not really an app necessarily, but oh, phooey. It's making me log in. Hope I can remember my password. It's debatable. Oh, I did. Hooray. What do you know? So the rules of the game in here, guys, is that you're supposed to know like some standard graphs as you go on, and maybe not in this course immediately, but eventually as you go on, you should be able, somebody tells you x squared plus y squared equals to 1, you should just kind of like know, oh, that's a circle, right? And later you'll learn if you put a minus here, it gives you what's called a hyperbola. We've already talked about, well, have we talked about? I don't think we have. We can also talk about graphs of lines, right? Y equals mx plus b. That's another thing that you're like expected to know, right? So there's a certain like standard list of examples of things that we should like recognize the formula as being something, right? But for other things, there's a wild world of things that we don't have names for, and yet we can graph them. And so that's what I want to share with you at the moment. Okay. So this costs you $0, which is good, right? And let's start out with what we just did. X squared plus y squared equals to 1. I'm pretty sure that's easier than your Texas Instruments, right? Now there is a difference. The Texas Instrument calculator, if you have it, or whatever, you can bring to the test, right? This is really just good for homework at the moment. But the other cool thing here is you can add a slider. Like I can add an A, and then I can see what happens if I make that number bigger, right? Or what happens if I make the number negative? There's no solution at all, right? Because we can't have the sum of 2 positive things work out to a negative number, right? So if that A is negative, no solution, but there you go. I told you if you put a minus here, you get hyperbolas. Check it out, yo. Hyperbolas. X squared minus y squared equals to A. And, well, here, check it out. You can animate it. Just hit play on your slider. Yay. You got hyperbolas that open up, hyperbolas that open sideways, right? If you want to get really interesting, you could even do something like 2xy. Add a middle term, see what happens. Whoa, yowzers. Well, that is way too big to see. You put an A here instead. Set this equal to 0. Ooh, we're too zoomed in to tell what's going on. Let me, zoomed out rather. Uh-oh. Oh no. Does this make sense? Why are we getting a pair of lines here? Can you guys explain that to me? If you can explain that to me, you're probably in the wrong class, right? In fact, I would be impressed probably with my pre-calculus class if any of them could just tell me immediately why this is happening. But the reason, I can tell you, see the formula? 2axy plus y squared? You can factor that into x minus ay times x plus ay. So the solutions are y is equal to x plus or minus x, y equals to x divided by plus or minus a, which is why we're getting two lines through the origin. And as a changes, the slope changes, which is what we're seeing. So here, let me make it more fun. There we go, that's what I wanted. So now that, oh my, look at that, what happened? Whoa. So now we're getting what? Hyperbolas? And it seems like when we go through a certain range of a, what happens? We get, yeah, like a squished circle, like an egg, right? This is called an ellipse. And there's a circle in there somewhere, right there, right? And then as we go this way, then we get an ellipse that goes the other way. But if you look at it, the ellipse is tilted, right? That's because there's this cross term xy in here. We actually never cover how to graph these in any of the pre-calculus or algebra classes. You have to take something called linear algebra to understand how to make these kind of graphs. So it's something that math majors cover like in their second year or something. Third year, I don't know. So you guys can make up any old equation you want. How about this? X squared plus y, y cubed equals to x minus 7. And I'll put an a in here just for kicks. See what happens. Apparently nothing so far. Whoa. Look at that. I don't even know. Do you know what to call this thing? I sure don't. Look at that. Oh, that's weird. I want to make a get bigger. Woo! All right, well, it's not so exciting. So what happens if you do like x? What happens if you do like x cubed plus y cubed equal to 1? What do you think that's going to look like? Let's get rid of this a. Why is it? Is that right? I did not expect that. What happens if we put a fourth power there? I think it may be. Oh, there we go. That's better. You can compare that to, there's the circle. What happens if we put absolute value of x plus the absolute value of y equal to 1? You know, what do you think will happen if I put x to the 10th plus y to the 10th equal to 1? Where do you think it's going to fit in this picture? Inside or outside? Outside, right? You're right. And so, in fact, as you let this number here go to infinity, you get a square. So, actually, these are all examples of circles as we define circles in abstract mathematics. Like, to some mathematicians, each one of these things is a circle because it's the set of points which are distance 1 from the origin, but not with respect to the notion of distance that I had covered up and just confused you guys with earlier with respect to another notion of distance. So, I don't know. I think it's interesting, but you don't have to. I was just trying to illustrate how we can use Desmos to do some graphs. Anything else you want to graph while I got this open? How about a line? What's a line? Y equals what? Mx plus b. We'll add slider for m, add a slider for b, and then we can do what? If we change b, it moves the y-intercept up and down, right? See that? And m, if we make m bigger, the slope is steeper, right? If we make m close to 0, it gets really shallow. At 0, it's a horizontal line, and when it's negative, it slopes the other way, right? So, anyway, just wanted to share some of those things with you. Let's look at a few more examples here before I close this. How about x squared plus x to the 4th minus 3x cubed? There's a graph, right? And how about y equals x plus 2 cubed plus 1 divided by x squared? There's another one. So you guys can see those, right? Let me change the color on this one. Oh, come on. There's a way to change the color on these. Oh, there we go. All right, so there's a couple of examples. What if I had like y equals to x over 2 minus 1? All right. There we go. And then finally, I'll put back in our old friend x squared plus y squared equals to, this time I'm going to put 100. I'll put 36. Right. All right. So technically, everything I have up here is the graph of an equation, right? So if I write y equals to x squared plus x to the 4th minus 3x cubed, or if I write y equals to x plus 2 squared plus 1 over x squared, or if I write x squared plus y squared equals to 36, all of these are equations, right? And we're looking at the graph of those equations, okay? But the thing I want to introduce to you next is the concept of a function. What is a function, right? And so functions are a little bit more special. I'll leave this up and so I have to hold my breath when I don't put a mask on, which is not a good idea for me, honestly, at this point. Then I get up here, I spray the board, and then I try to breathe deeply. You should never inhale this. It's not good. Trust me. It also doesn't taste good. Go figure. All right, so what is a function? F. So I'm going to be a little bit abstract. I need to be a little bit abstract for a little bit, just to make sure the definition of function is made correctly, and then I'm going to specialize back to the land of y and x and such, okay? But to start with, I'm going to be just a little bit abstract. And so f is a function from a set A to a set B is a function from A to B if whenever x is in A, we have f of x is a single element of B. Um, the domain of F is A, and that's also the set of possible inputs for F. The codomain of F is equal to B, and this is the set of possible, well, now I've used possible, and this is an unfortunate terminology I've used. Maybe I should cross out possible and use actual here, perhaps. That language would be better. Because these are the actual inputs for F, whereas the codomain is the set of like possible outputs in the sense of it has to be in there somewhere, but it doesn't actually have to be there. Let me use different language. It's the set where the outputs have to go. In contrast, the range of F is probably what you're thinking of. This is equal to the set of outputs for F. To be more precise, the range is f of x such that x is in the domain of the function. So let me just, I find this picture is comforting. You can agree or disagree, whatever. But here's A, here's B. F is something that goes from there to there, like that. And so it takes a point here, x, and it moves it over to here, a point f of x. But, so the codomain is that big box. The range, it doesn't have to be the whole thing. It could be like a subset of B. So the range could look something like just like this, perhaps. The domain has to be the whole of A. That's just the way we make the definition. But the range doesn't have to be the whole of the codomain. Let me give you an example. We could have A is equal to the set containing 1, 2, and 3. And we could have B be the set containing dog, cat, and Naruto. You guys know Naruto, right? You studied the finer things. No? You guys are not classically educated? It's a very popular Japanese cartoon. But anyway, I could say f of 1 equals to dog, f of 2 equals to cat, and f of 3 is equal to dog again. Or I could also draw the picture like this. 1, 2, 3, dog, cat, Naruto. So your book sometimes likes to make little arrow diagrams to illustrate what the function does, right? Since it's a function, it has a single output for each input, which means when you start on the left, you only draw one line per input. So like 1 goes to dog, right? 2 goes to cat, right? And 3 goes to dog again. So what's the range of this very silly function that I'm sharing with you? Well, I'll do the easy part. What's the domain? What are the allowed input, the actual inputs for the function? I will start saying possible inputs. I'm just You guys gonna make me do all the work. I'm gonna get your name on cards, then I'm gonna start naming names. Your time is up. Your time is coming. It's next on my list of things to do. 1, 2, and 3. Okay, yeah. 1, 2, 3. But once I get those cards, I'm gonna start asking hard questions. Let's see here. I'll teach you. Let's see here. Leave me up all alone up here. I see codomain. What's the codomain of F? It's dog, cat, and Naruto, right? What's the range? The range is just dog and cat, because those are the only things which are actually mapped to. Naruto's off on his lonesome. He never gets mapped to by the function. You're like, well, why'd you put Naruto in the codomain? That's stupid. The function's got nothing to do with him. Sorry, that's just the way we talk about functions. We like to put the codomain being bigger than we need so we can just sort of anticipate possibilities. All right? Let me show you an interesting example where the idea of codomain is kind of like, more easy to understand why we want such an idea. How about this? Suppose we have f of x equal to 1 over x squared plus 1. Where f is a mapping from the reals to the reals. So you guys know that when I write this, I mean minus infinity to infinity, right? Well, if you don't, I'm telling you, that's the whole real numbers. Oh, the camera, thank you. Oh, I moved it. You were taking notes and I did that. Okay, so what's the domain? I mean, apparently, once I write this, you know what the domain is. I mean, I gave you the domain for free here. The domain is the real numbers. The codomain is also the real numbers because I wrote this here. What's the actual range, though? How would you figure out the actual range? We need to graph, right? We need to graph 1 over x squared plus 1. So what do we get? See that? That black line there? That's the graph. So I'll reproduce it over here because I don't want to move the camera over, but we just graphed it, and we saw that this guy is kind of like a mountain. And if you studied it, you'd see its y-intercept is 1, and it goes like that again. So I gave you this kind of like abstract definition of a function, right? Let's try to reinterpret some of those words as they relate to when a function is going from the reals to the reals, and we can look at its graph in the xy plane, right? The set of possible inputs for f is what? It's really the x values in the graph, right? And the set of the codomain is not really on the graph, but the range is the y values attained by the graph of f. So this point right here is 0, 1. And so if you look at it, it never gets to 0, right? If you set 1 over x squared plus 1 equal to 0, you won't get a solution, right? Try this out. what happens when we solve this? We get what? Multiply both sides by x squared plus 1. Cross multiply if you prefer to say it that way. We get what? We get 1 equals to 0 times x squared plus 1. What's 0 times x squared plus 1? 0. 1 equals 0. This is false, right? That tells me that there is no solution to 1 over x squared plus 1 equal to 0. That tells me that the graph of this function does not cross the x-axis. There's no place where y is equal to 0 in the graph. Now, we already saw that with the Desmos, right? It asymptotically, these are asymptotes, okay? It asymptotically approaches y equals to 0. Yeah, go for it. Go. So what's the range? Can you guys tell me? Oh, sorry. I probably should have left that. Anybody need me to rewrite that? Are you guys okay? Rewrite it? Okay. So if we set the formula for the function equal to 0, we find out we can't solve it, which means that there's no place where the graph crosses y equals to 0. Y equals to 0 is the x-axis. So I'm just doing algebra to verify what I can already kind of see in the picture that Desmos created. I mean, well, that's the thing. With the Desmos, if you zoom in, if you're zoomed out, it kind of looks like it gets to the x-axis, doesn't it? But that's an illusion. It doesn't actually get to the x-axis. That's just the limit of the resolution of the picture, right? The x-axis and the graph get conflated. They get confused. They seem to overlap when we're zoomed out. If we were to zoom in on that, we'd see that the graph, the black graph, and the x-axis were separate. Okay, going back to my question, what's the range of this function? No, the range should be, let me put it, I want the range in interval notation. One is the upper, one is as big as it gets, right? So 1 is included too, right? Because f of 0 is equal to 1. That's tops, right? That's that zenith, top of the hill, right? What's the smallest, yeah? Go ahead. All numbers greater than 0, but less than or equal to 1. Yes. So we do 0 not included because it asymptotically approaches 0, doesn't get there. That's the range. So like, pragmatically speaking, right, guys? If you've got a function and you just want to like say, okay, I've got a function. It goes, from this set to this set. Maybe I can see what the domain is, right? But I don't want to commit to the range being a particular thing. I know that the range is some subset of real numbers, but I don't want to commit to which subset of real numbers. That's what this codomain allows me to do. I just say, okay, well, it's here somewhere. And I could make this smaller, right? But if I don't want to, and I just want to have a way to refer to it, I just leave it bigger, and then we can come back to the range and pin down exactly what it is. Roughly speaking, the idea behind codomain. I will admit, as a student, it really bothered me. I always felt like, why are you talking about codomain? You should just make the codomain the range, because that's where it actually goes to, Why are you leaving this extra wiggle room that we don't actually use? It's annoying, But it is. There it is. By the way, your text briefly mentions if you have something that's like a function, but a single input can go to more than one output, then that's what's called a relation. So like a relation could output more than one thing from a single input. But a function, the key property is that it outputs just one output for each input. Now those outputs can be the same for different inputs. That's allowed. Like 3 and 1 both go to dog. But what I couldn't have is I couldn't have one go to both dog and cat at the same time. That would not be a function. Now, what does that mean for graphs in the xy plane, right? What does it mean graphically that a function can only have one output for each input? What does one output for each input look like for a function? So by the way, I should probably give you a definition. If f is a function on R, so a function on R, what this means, that's just language to say that both the domain and the codomain are subsets of the real numbers. So that means it's like inputting real numbers and it's outputting real numbers. Okay? F is a function on R. Then the graph of f is the set of ordered pairs x, comma, f of x, such that x is an element of the domain of f. So the graph of a function is a subset of the plane where the equation y equals f of x is true. In other words, aka the graph of f is a subset of R2 where y equals to f of x and x is in the domain. This is what we mean by graph. That's really the same as the definition of graph I gave you at the start of class, right? What was the graph of an equation? It's a set of points x, y, which make the equation true, right? Now I'm just telling you that the graph of a function is the set of x, comma, y that makes the equation y equals f of x true. It's really the same idea. It's just specialized to f being a function. So let's see here. So my question to you is, what does this mean about, like, when we picture the graph of a function? What does it have to look like? Let me just put a hypothetical up here and try to explain to you why there's something we must avoid. So I'm going to ask a loaded question. Can the graph of a function look like this? You say no, but why? Why no? Because I'm still getting used to the class times in here. So we start at 1:25, right? Which means I have till 2:40. So it's 3 then, right? No. Someday you guys will agree to it. So 2:40. Okay, great. We're fine. We have plenty of time. So on this picture, where can we visualize the input? So if this is a point on the graph, right here, it's a point what? X, comma, f of x, right? If this blue line is y equals f of x, you know? So in other words, I can think of the input being here, and then the output it takes me up to that point, right? You can think of the function in that way. It takes the x-axis and it pushes it up or down to the graph of the function. So you're saying, I heard some grumbling about this here, right? So if this was 5, and say, I draw this vertical line over 5, right? I've got 1, 2, and 3. I've got 3 separate points allegedly on the graph of this function. So in order for that to be like, let's suppose that those are at like 3, 4, and 5 for the sake of. So that would mean that f of 5 is equal to 3, but it would also mean that f of 5 is equal to 4. It would also mean that f of 5 is equal to 5. This is not allowed. We cannot have one input and give 3 outputs. What that means for the graph is that means that when we're looking at a picture of a possible graph of a function, it's not actually a graph of a function if it fails the vertical line test. Right? What's the vertical line test? Each vertical line through a point in the domain of f of x must hit just one point on graph. Of course, another way you could say this is if you look at all possible vertical lines, every one of those vertical lines hits at most one point on the graph. You could just throw in all the vertical lines which aren't even hitting the function. Those would hit 0 points, right? You could say it that way too. So every vertical line hits at most 1 point in the graph. That's a vertical line test. That vertical line hit 2 points, right? So now that we've done that, what about the circle? Is the circle the graph of a function? It's not, right? Because if we make a vertical line through that circle, we're hitting what? 2 points. Of course, if you go back to the algebra we did at the start of today, you kind of see that. Let me just revisit that for a minute. So we had x squared plus y squared equals to 1, right? And I pointed out if we solve for y, that gives us y is equal to plus or minus the square root of 1 minus x squared. So you see, the algebra is already telling us it's not a function because we couldn't just solve for y, right? We had two things, plus and the minus, right? So if you look at y equals to square root of 1 minus x squared, or if you look at y is equal to minus the square root of 1 minus x squared, these guys separately form the graph of a function. They can be looked at as a function. Like a picture of it is just this. We can take the plus square root for the upper half circle, right? Does that pass the vertical line test? Does, yeah. What's its domain? You notice all of a sudden I'm not telling you what the domain is. I just did what? I wrote a formula down, and now I'm asking you to, from the formula, figure out the domain. That's often what's done. So the domain, so if this is equal to f of x, the domain of f is minus 1 to 1. So that would be a function. What's the range? This point up here was 0, 1.